Okay, good morning again. This time I will give you an example of ray diagramming and mathematical calculations in this time a concave lens. Okay, so again, just like before, you start with the principal axis. You have to draw the principal axis. You have to make it as straight as possible, like so. And then after that, you choose a point at which you will put your lens axis in. So I will choose somewhere at the center here. Again, I just have to make sure that this is completely perpendicular. Otherwise, you might get errors in your ray diagramming. So, like so. And then since this is a concave lens, we will draw the concave shape of the lens. But again, this is not so difficult. Unlike the mirror wherein the curve should be, the curve of a circle, this time it doesn't need to be, at least for array diagramming purpose. Again, if you are trying to make a lens out of glass, for example, then of course the shape, the curvature of the edges of the lens would matter. Okay, and then from there we can now choose, you can now decide on the length of your focus. Okay, so I'm just going to measure some length of my focus here, something like 2 inches. So maybe here. And then 2f would be twice the length of the focus, so another 2 inches there. So and then I'll mark these points as f and 2f. Right, so that goes also on the to the other side of the lens. So you will find the focus here, 2 inches away, and then another 2 inches away from that will be your 2f. So this will be f, this will be 2f. Okay, class, always remember that for a lens, the focus exists on both sides because again, a lens is transparent. So if light rays come from here, then there's a focus on the other side. If light rays come from the other side, there's also a focus on the other side. Unlike the mirror, where the mirror is really the curvature of a circle, and where the curvature of the circle is, halfway to that is the focus. So therefore, the focus could either be inside the mirror or outside the mirror, depending on your perspective, on which the reflecting side is used. If it's the concave shape that is used the reflecting side, then the focus will be outside that mirror, in front of the mirror. But if it's the convex side that is used as a reflecting surface, then the focus will be on inside the mirror, not outside the mirror. But for lenses, it's not trivial. You can put the focus on both sides of the lens because again, it's a transparent material. It can allow light to pass through it anyway, so it doesn't matter which side is used. Okay, and then now we will choose, and now you will choose the object. First, we will choose a case. So this time we will choose a case that we have not done before. So I believe I have not chosen a case that is at 2f. So I will choose um, case number 2. This is a concave lens. This is case 2, which is the object is at 2f. So the object is at 2f itself, at the 2f point. And then here you get to decide again the height of the object. And this time I will make it a little bit bigger. So maybe as big as I can. So 2 inches probably. And again, you have to make also your object really perpendicular to the principal axis. You don't want to draw your object, that you don't want to draw your object sloping this way or that way because that will affect how you draw the diagrams. Okay, so that's the object. So what do we know here? Well, we know the f again. So the focal length is from here to here, and I have measured that, we have measured that to be 2 inches. Okay? On both sides, from here to here or from here to here, that's 2 inches. And then we know the object distance. How far is the object placed in front of the lens? And that is, well, this is 2, that's 4. So at 2f means 4 inches away from the vertex. And then finally, we know the height of the object. And I made this, if you remember, I used 2 inches. I measured 2 inches to have this height. Let me confirm that. Maybe, yes, that's 2 inches. And that's what we know. And again, in order for us to gauge what the image will be, we kind of have to know two things. We have to be able to uh, calculate the q, which is the image distance, and the h prime, which is the image height. Okay, so this time let's just for fun, let's make it reverse. Let's calculate first the values, and then before we do the ray diagramming. Okay, so again, I'm just going to start here because I want to save space, and maybe I will continue it here. So for example, so the first one is, of course, um, calculating for the q. So we will use the inverse of the focal length is equal to the inverse to the distance, to the object distance, plus the inverse of the image distance. And again, I want to solve for q here, so I want to isolate 1 over q, and that would be 1 over f minus 1 over p. And again, these are two terms. I don't want that to be two terms. I want that to be a single term, so I'll join those two. That's the common denominator. Fp divided by f is p. Fp divided by p is f. So 1 over q, therefore, is p minus f over f times p. And again, I don't want 1 over q. I want q. And q is simply the inverse of 1 over q. So you take the inverse of this, and that should give you q. So if I take the inverse of this, this will be p times f over p minus f. Okay? So this one, that's what I will continue to solve, and I will write it here. So q is therefore fp. What's f? F is 2 inches. And then q, and then p is 4 inches, because that's 2, that's 4. So 4 inches over p is again 4 inches minus f is again 2 inches. Okay? However, there's a tricky part here, and the tricky part here is to realize that you are dealing with a concave lens. Therefore, it has a virtual focus. Okay? Remember, a virtual focus, it means that if you have light rays coming from here, the light rays will scatter and they will never meet. So what you do is you retrace back the light rays and put the focus here. Okay? That's a virtual focus. That's different from a real focus, for example, a convex lens, where the light rays come from here, they get converged, and then they meet here. So they really meet at a point. So that's a real focus. Now this one, that means they don't really meet. What we're doing is we're just retracing back the lines to make a focus. Meaning this is not real. So this is imaginary. So if it's imaginary, what that means is it will be a negative focal length. So therefore, that means that we have to modify this. The focal length is not 2 inches, but it's negative 2. Because again, negative 2 inches, that means it's a virtual focus, because this is a concave lens. The P is okay. It's 4. The H is okay, that's upright, so that's 2 inches, but it's the focus that is should be -2. So if that's the case, so this should be -2, and this should be -2 as well. So what that means is if you multiply this 2, this will be 2 times 8, that would be -8 inches squared, divided by 4 inches minus -2. Remember, minus -2, that means plus 2. So this becomes 6 inches. And then from there, this inches will cancel out with one of the inches here, so it will remove the exponent. So now we'll have -8 over 6, right? So -8 over 6 is of course 4 over 3. 4 over 3 is 1 and 1/3. So therefore, this is 1.33, and this is non-terminating. So that's the Q, and take note, this is negative. Negative. So again, just remember that this is, we rounded it off here, but this should be 1.33333. This is a non-terminating um, number, non-terminating repeating number. Okay. Now, how about, so we now know the Q, which is negative 1.33 inches. So now we will solve for the H prime. So H prime is H prime over H is equal, so we use a magnification equation. H prime over H is equal to negative of Q over P. Take note that that negative is inherent to the equation. So it's already there. So you don't remove that. It's in there in the equation itself. So if I want to solve for H prime, this would be negative Q over P times H, just like before. And then now I can replace, so negative, and then the Q is negative 1.33 inches, right? So take note that this negative is inherent to the equation. Then the Q itself is a negative number, so it's negative of negative 1.33 inches over P, and I know our P is positive 4 inches. And then you multiply it with the height, which is your 2 inches, which is also positive because it's going to the top. So if you are going to measure the height from here to the bottom, then that's a negative height, but this is a positive height. Okay? And so now what we can do is we can now calculate this. And again, I'd like to think that 1.3333 is 4 over 3. So 4 over 3 times 2 would be 8 over 3, right? And would be 8 over 3. And 8 over 3 is around 2 and 2/3, so 2.6666666666, right? So this will become, I will not change the negative side, I will just have this. So that would still be negative 2.66666667. This is again non-terminating, and then this is inches squared over 4 inches. And again, the inches here will cancel out with the one of the inches in the inches squared, because remember, inches squared is inches inches. So basically this is inches over inches, so one of the inches will cancel out. That means what is left is just inches without the exponential term, or without the exponent. And then now I have the H prime. So take note that this is negative and negative. So negative and negative, that means it is positive, right? And then that is divided by 4. And finally, we get 0.6666 non-terminating. So basically 2/3, 0.67 inches. And mind you, the negative disappears because that's negative and negative, so this is positive. Okay? So basically, using our mathematical calculation, we know that Q is negative 1.33 inches and the H is positive 0.67 inches. Okay? So now we can find out the lost, or we can evaluate the lost. Lost is location of the image, orientation of the image, size of the image, and then type of the image. So for the location of the image, take note that it is negative 1.33. So negative 1.33, so 1.33 away, right? 1.33 away from the vertex. So that would be between the vertex and the V. It's on this side. I remember the side of the object is positive. So if the side of the object is positive, so negative 1.33 is towards this direction. So negative 1.33 is between V and F. So the location is between V and F. Now how about the orientation? Well, we can look at the sign of the height. If the height is positive, that means it's upright. If the height is negative, it's inverted. So this is positive, so this is upright. How about the size? Well, we just compare the original height, which is 2 inches, to the image height, which is 0.67. So if you notice, 2 to 0.67, that means the image is diminished in size. So we call the size as smaller. It's smaller than the original object. Then how about the type? So the type is about the Q, and it revolves around this sign here. Okay, so this sign here, I'm sorry, I was mistaken kanina. When I explained about the location, when I said negative 1.33, I said negative is on this side. No, I was wrong. Negative is on this side, which is this one. Nga naman sir, I thought positive is a side's object. I will explain later. But I made a mistake. But that negative 1.33 is in here, right? But the point is it's negative. So what does it mean to be negative? Well, it's just like your focus. Remember, if you have a virtual focus, it's negative. If you have a real focus, it's positive. So the fact that the image distance is negative, it means it is not a real image, but it's a virtual image. So now we can therefore answer this as virtual. Okay, just by looking at the sign. I did not even have to draw. Remember, I found out lost without drawing the ray diagram. Okay? Now, let me explain why I said the negative side is in this side. Okay? So, class, I think about it in terms of what is the normal side. Okay? Because for a mirror, if you have a mirror, this is the reflecting side and this is the object. So the light rays from the object hits the mirror. We know that a mirror is opaque. So the light rays that hit it should bounce back and return on the same side. So if the light rays came from here, it reaches the mirror, it gets reflected, it should return on this side. So therefore, we know that the normal side for the image should be in front of the mirror. Because after all, light rays are reflected back, right? So when light rays are reflected back, yet the image is formed not in front of the mirror, but somewhere inside the mirror, that's when we say it's a virtual image because it's not real. Light rays could not have come from there because this is an opaque object, remember? So that's how I think about virtual and real images. Now for a lens, it's different because remember a lens, the action of a lens is to allow the light to pass through. Meaning, if the light rays are coming from here, it is expected that the light rays really go pass through the lens and meet here. Therefore, for a lens, the normal side for a lens is the opposite side, right? Think about what should happen. What should happen is the light ray should penetrate the lens and meet here. So therefore, this is the normal side. So when you get a positive image for lenses, it should be on the opposite side. a negative side means it's in a place where it's not supposed to be. So the fact that the image is negative, it means the object is here, the light should pass through, but somehow the image is on this side. That's why we gave it a negative sign. Okay? So that's how I rationalize that. So again, this light ray, this object, light ray should pass through and form the image on the other side. That's the normal side. But the fact that the image sign is negative, that means it's not in the normal side. It forms here. Okay? Now you might say, oh, tinood na sir, dito siya, dito siya ma-form or posible man. Well, we can confirm by doing the ray diagram, because you know the mathematical method is very mathematical. We don't see visuals in it, but the moment you do ray diagrams, then you can really see if the image is really formed on the side that it's not normal for a lens. Okay, so let's do that. So remember the rays. The first ray is a PF ray, so it's a ray that is parallel. It's a ray that is parallel to the principal axis. So from here, parallel, it should reach the lens axis, meaning here at the center. You don't stop when it hits the surface. You stop when it hits the uh, these lens axis. So this is the lens axis. Let's label that. And then once it hits there, remember, parallel focus, PF. So what should I do? Should I do it like this? No, because think about it. This is a diverging lens. Remember, it will scatter the light rays. So if you have a light ray from here and then it goes down, that means the light rays are not scattered. The light rays are converged. So common sense would tell us that the light ray should somehow shoot up because it is scattered. Okay, so that means it doesn't pass through here. What we do is it will align with the focus on this side. It will align. It will align. That means you put your ruler like this, align the 2 points, and then start here, and then draw the refracted ray. So it will align. Another way to think about this is to say that, well, a concave lens has a virtual focus. Virtual focus meaning its focus is not on the other side. So the light ray should not pass through the focus on the other side. However, it should align with the focus on the same side as the object. So this will, and just for emphasis, let me, well, it's like that. And then the next one is the V ray. Remember, a V ray is a ray that starts from the top, passes through the vertex, and it just travels as if nothing happens, as if there's no refraction. So it just passes through like that. Okay? And then you have the V ray, our FV ray, our FP ray. FP ray means it's coming from the top, it aligns with the focus, not aligns with the focus here. It aligns with the focus, right? It aligns with the focus on the other side like that. And then when it reaches here, it becomes parallel. Okay? So let me align. Again and again, I have to stop once I reach the lens axis. Once I reach the lens axis, I will now make a line that is parallel to it. Parallel to the principal axis. So like so. And that's it. You only remember, in lenses you only have 3 rays, unlike in mirrors. Okay, so if you notice here, this light ray, that light ray, and that light ray, they diverge. Well, that's to be expected. Remember, because um, light rays should diverge when you have uh, a concave lens. Okay, So if I move them forward, they will not meet, they will not form an image. But when I move them backwards, they will meet. So therefore, that's the next step. We have to trace the refracted ray backwards. Remember, there are two parts here: the incident, which is going towards the lens, and then the refracted. Always retrace the refracted rays. So again, I will align this with the focus. And since this is a PF ray, obviously when I retrace it, it should pass through the focus like so. And then how about this V-ray? Well, this V-ray is incident and refracted. So if I retrace, it just retraces back to the same line. So I don't need to retrace it because there's already a line here. And then the FP ray, this is the F, the incident ray, and then the refracted ray. Again, you will retrace the refracted ray. So you will retrace this one. And if you retrace this one, okay? So you notice, where do they meet? The all three rays meet. They meet here. And if they meet here, that's the head of the arrow. So the head of the arrow should be formed there. And since the foot of the arrow is on the principal axis, then the foot of the arrow should be also the principal axis. So now that's your image. And this is now your object. So let's review the lost. Sakto ba? According to our mathematical equation, lost, the L should be between V and F. Yes, it's between V and F. How about orientation? It should be upright. Well, look at that. The object, the image is upright. How about the size? It should be smaller. Well, this is the object and that's the image, so it's smaller. And lastly, it should be virtual. Virtual means it should be formed when you retrace the light rays. Yes, it's virtual. Okay? So you see, class, um, whether you do ray diagramming, which is a more visual approach, or you do mathematical calculation, the answer should be the same, barring, of course, errors in your drawing and and something, and maybe how you round off the things. So for example, right now we can measure, because here we said that the Q is negative 1.33 inch. So if I measure this one, it should be 1.33 inches. And look at that. This is the 0 part, like 0 to 1 inch. This is the 2. So if you divide the this inch into 3, that should be somewhere, should be somewhere where the 1.33 lies. So the Q is is spot on. How about the height? According to our calculation, the height should be 0.67 inches. So if we measure this one, look at that. That's 0, this is 1. So this is 1/3, 2/3, 3/3. So notice 1/3, 2/3. The height is our 2/3 the inch. So 2/3 means 0.67. Okay? So it works. Ray diagramming works. Now, again, I have to warn you that when you draw the incident ray, you have to move it all the way to the lens axis before it changes directions. Okay? Now, for the more perceptive of you, that might uh, you might ask a question like this: Sir, naglibog ko, sir. Abi ko, niingon ka. You said last time that if a light ray enters the boundary between two materials, so this is air here and this is glass. So now it enters the air and glass, air glass boundary. And then here, when it exits, it also exits the glass and air boundary. So you might saying, sir, when it hits the um, glass air boundary, it will bend like this. And then when it reaches the boundary na pod between glass and air, so this is air and glass boundary, here glass and air, it will also bend like so. So dapat kaduha ni bend, sir. When you have something like this, it should be something like here, it bends, and then when it reaches here, it bends. There should be two changes in direction. And yes, you are correct. In the real world, that is what happens. What we are saying is that is too difficult to do. This is too difficult to do. So what we are saying is if you just impose that this light ray, instead of bends at the boundary, enters the lens, hits the lens axis first before it bends, you will still get the same result. Okay, you will still get the same result. So what we're saying is this is just an approximation. So for us, so that it's easier for us, we just assume that the light ray never bended when it crossed the boundary, that it only bends or changes direction when it reaches the lens axis. But yes, you are correct. It should be two changes in directions, but we are kumbaga, we are doing a shortcut. We are doing a technique that approximates but still gets the correct trajectory of the light ray that's coming out of the lens. Okay, so again, last time, instead of changing direction once and then changing direction twice, what you can do is we can impose that this you have this lens axis, then the light ray is just assumed to be straight, and then when it reaches here, it now changes direction, and the result is still the same direction. So it's an approximation. Okay, so I hope that uh, clarifies what you should do. You should do ray diagramming, you should do the calculations, and the calculations, the results of the calculations, the loss determined by the calculations should be the same as the loss determined by the ray diagramming. So we are in a way trying to confirm that your ray diagram is correct through mathematical calculations. Okay?